Okay, welcome to the lesson on relationships within tables. I want to bring your attention to this picture here. What do you think it does? What is that thing? What is that contraption? And what does it have to do with relationships within tables? So our goal here is to demonstrate an understanding of the relationships within tables of values in order to solve problems. You'll need your note pack or a blank notebook and a pencil, and you may also want a ruler and maybe some linking cubes. So go ahead and get those now. Okay, here's my notes, here's my ruler, and here's my linking cubes. Let's begin by making a connection map. So what does this remind you of? Relationships within tables. As always, words, pictures, connections within math, connections from the real world, connections from school. Go ahead and take at least 5 minutes to make as many connections as you can. Okay, here's an example of what that might look like. I made some connections to the word relationship, things being related to each other, like people and marriage and dating and children and cousins. They affect each other within, inside, and tables. Tables of values, horizontal, vertical, how X relates to Y. So what was that thing? It was an input-output machine. I'll shift your attention to this arrow that goes in here, and then all this stuff happens, and then this arrow that goes out here. So the idea of an input-output machine is that you put a number inside the machine, something happens, and then a different number comes out. And this is the metaphor we're kind of using to draw our attention on the thing that happens within the machine. So I have a few examples for you. So if you put the number 1 into the machine and then 2 comes out, what's happened inside the machine? Well, the most simple rule is that the 1 was added. So 1 went in and 2 came out, so the rule must be to add 1. What about this example? You put 5 in and 2 comes out. What do you think the rule could be? Be aware there's some more than one correct answer for this, but I think the most straightforward rule in this case would be subtract 3. How about here? You put in 5 and 15 comes out. What are some rules that might apply here? One rule you might say is to add 10, and that would be correct, but in this case, the idea here is to multiply 3. And we'll come back to this idea of how do you prove which rule is the actual rule later in the lesson. What about here? 20, and then out comes 10. Well, in this case, the idea being we've divided by 2. All right, so those are some examples. So what we're focused on is how to record that input-output machine as a table. So you can see here's the machine. When something goes in, something else comes out. So in this case, when 1 goes in, 3 comes out. That's why this says in, this says out, or X, Y, input, output. These are all the same thing. So the left column shows what's going in. So the 2 goes in, what comes out? The 6. Okay, so when a 3 goes in, what comes out? A 9. 4 goes in, 12 comes out, 5 comes in, 15 comes out. So the question is, what is the relationship rule in this case? Well, there's a few options. First off, maybe you think that it's plus 2 because 1 plus 2 equals 3. Well, does that work for the second row? 2 plus 2 equals 4. So that doesn't work. So let's go back and make another hypothesis. This number is getting bigger, so maybe we try multiplication. 1 times 3 is 3. Okay. 2 times 3 is 6. Okay. 3 times 3 is 9. There we go. So this looks like it's working. 4 times 3 is 12, and 5 times 3 is 15. So what is my relationship rule? Went ahead and filled this in. So my relationship rule was to multiply by 3. 1 times 3 is 3. 2 times 3 is 6. That's what's happening inside the mysterious input-output machine. So what is the relationship rule? Well, you could write it as a sentence. Multiply the input by 3. or you could write it as an equation with words, 3 times x equals y, or you could simply write 3x equals y, because this means that 3 groups of the input equal the output. Make sure to fill in your sheet now if you haven't already. So as you can see, we have the relationship rule in the middle column, and then the relationship rule could be multiply the input by 3. Okay, what about this rule? 2n plus 1 equals y. So what do we mean by this? We mean 2 groups of the input, which in this case we're calling n, plus 1 more equals y. Okay, so let's think about if n is 1. So we have 2 groups of 1 plus 1. So 2 groups of 1 makes 2, and then 1 more makes 3. So when the input is 1, the output here is going to be 3. What about when n is no longer 1? It's now 2. So we have 2 groups of 2 plus 1 more. So 2 groups of 2 is 4, plus 1 more is 5. So my output is now 5. Okay, moving along, what about 3? When n is equal to 3, well, let's see if we can use some mental math here. 2 groups of 3 make 6, plus 1 more is 7, right? So 7. Now, are we seeing a pattern here? 3 plus 2 more is 5, plus 2 more is 7. So I'm noticing, and I'm predicting, that this next number is going to be 9, right? 3, 5, 7, 9. But let's see whether that's true. Okay, so when n is 4, we have 2 groups of 4, and then 1 more. So that's 8. And then we have 1 more. That is 9. Great. So our prediction looks like it's correct. And when n is equal to 5, it should be 11. I'll use some mental math to check. 2 times 5 is 10, plus 1 more is 11. Okay, so there we go. Go ahead and fill in that table. Okay, now we're going to look at an example, and it's an active example. This is Daniel and Maize dance. So a dance group created a dance to go along with a song that has 10 parts. There will be 2 dancers in the first part, and then for each new part, 3 more dancers will join in. The question is, how many dancers will be on stage by the end of part 10? If we're in class, we're going to actually act out this dance. If you're at home, I don't know, maybe get a bunch of little figures and you can play a song and put in 3 more figures dancing every part of the song. So go ahead and act that out. All right, so these 2 guys are dancing. 2 dancers to start. All right, oh, part 2's coming. Oh, now we have 5 people dancing. Oh, here comes part 3. Whoa, now we have 8 dancing. All right, I hope you had fun with that. So here's Daniel. Daniel said that he'd use yellow cubes to show the 2 starting dancers, and then red cubes to show the dancers coming in. So you can see in part 1 there was 2 dancers, and then part 2 there's the original 2 plus 3 more. In part 3 you had the original 2 and the 3 that had already joined plus the new 3, and so on and so on. And then after using the cubes to make a model, he made a table. Right? So for the top row we have part number, and for the bottom row we have number of dancers. So it starts with 2, and then there's 5 dancers, then there's 8, and then there's 11. And Daniel decided he would just extend the pattern all the way to part 10. So here we go. Part number of dancers. Gets 3 new dancers every single time. And then by the end of part 10, we have 29 dancers just rocking out on the stage. So that's one way of solving this problem. We'll also look at Maize Rule. So Mai's thinking, well, the number of dancers increases by 3 each time. And if there were 3 dancers in part 1, then the number of dancers would always be 3 times the part number. But part 1 has 2 dancers, so I'm going to need to make a 2-step equation. I made a column in my table showing multiplying by 3, and I noticed that the number of dancers is always 1 less than the 3 times the part number, right? So 1 times 3 is 3, but 2 is 1 less than 3. 2 times 3 is 6, and 5 is 1 less than 6. 3 times 3 is 9, and 8 is 1 less than 9. 4 times 3 is 12, and 11 is 1 less than 12. So she can write this pattern rule. Multiply the part number by 3 and subtract the product. Or 3p minus 1 equals d, where p means the part number and d means the number of dancers. So for part 10, which is 10 times 3 equals 30, and then 30 minus 1 is 29. Okay, so to review. 1, we can imagine an input-output machine. 2, the relationship rule is what happens inside the magical input-output machine. 3, inputs, outputs, and relationship rules can all be represented within a table. And 4, finding relationship rules helps to solve more complex problems without having to make a huge table. So in this case, if the input times 3 is the output, then for 100, you would know that the output is 300. We have 1-step equations and 2-step equations. 1-step equations only have one operation step. For example, subtract the input by 3 is a 1-step equation. 1-step equations are simpler to recognize. 5 minus 3 equals 2. 2-step equations have 2 operation steps. For example, multiply the input by 3, then subtract 1. That's a 2-step equation. They can be much more difficult to recognize. And a strategy is to find out how much the term changes by each time, and then use that as the multiplier, and then from there add or subtract. So in this case, we notice 2 plus 3 is 5, 5 plus 3 is 8, 8 plus 3 is 11. It's increasing by 3 each time. So we can multiply by 3 to get that, and then from there, figure out what the rest of the rule is. In this case, it was multiply by 3 and then subtract 1. All right. So let's look at an example. Find the rule and complete the table. So we have input, output. We see that when the input is 9, the output is 3. When the input is 14, we don't know what the output is. When the input is 16, the output is 10. When the input is 17, we don't know what the output is. On and on. Okay, so here's how we would solve this. We would have to use the complete rows to find the rule. The rule makes each number decrease, so let's try using subtraction. So starting with the number in the in column, we're figuring out what number is subtracted by to get the out column. So in this case, 9 minus 6 is 3, 16 minus 6 is 10, 18 minus 6 is 12, and 20 minus 6 is 14. So because that rule works for every single case, that's the rule, subtract 6. Next, you use that rule to find the missing number. So in this case, 14 minus 6 is 8, and 17 minus 6 is 11. And then you write the answers in the table. Next, we have a 2-step equation example. So they ask you to read the following description of a relationship. A team of glass blowers makes 8 vases per hour. At the end of each workday, they recycle their 7 least favorite vases made that day. Let H represent the number of hours in a workday, and V represent the total number of vases kept from that day. And they're asking you to complete the equation that represents the relationship between H, which is the number of hours, and V, the number of vases kept. It gets tricky. So in this case, when the input is 2, the output's 9. When the input is 3, the output is 17. When the input is 4, the output is 25. And when the input is 5, the output is 33. So how to answer this? Read the description and find the relationship between the number of hours worked and the total number of vases kept. So the team of glassblowers makes 8 vases per hour, and at the end of each workday, they recycle their 7 least favorite vases. So in this relationship, H is the input and V is the output. Hours put in is the input. How many vases you have at the end is the output. So you find V by multiplying H by 8 and then subtracting 7 from the result, right? They make 8 vases per hour, so that's 8 times H, minus 7 at the end of the day. So here's our relationship as an equation, H times 8 minus 7, and then you have 8H minus 7. So here's my input, 2. 8 times 2 minus 7 is 9, so there's my output, 9. So the equation for the relationship is vases equals 8 times H minus 7. Now I hear you out there. Mr. Locking, this is crazy. I just learned what a variable is. What is happening? I get it. I get it. I get it. I get it. This is one of the hardest outcomes in grade 6, but we'll get there. Don't worry. Okay. So key practice is to work with input-output tables. So there's grade 6 M7, which is similar to the first example. There's grade 6 Z5, which is similar to the second example. And then on IXL, you can actually search input-output tables, and then you get a whole bunch of different skills. And so if these ones are too advanced for you right now, then please do one that is more within your zone. Totally, totally fine. The more you practice with this, the more it will make sense. And then your key problem has to do with guitar lessons. So the table below shows how much a guitar lesson costs if you also pay at the start to rent a guitar. So at your first lesson, the total cost is $80, but at your second lesson, the total cost is $110. And so with that information, you can kind of see, oh, how much was the guitar rental and how much is the per lesson cost. And then the question is, how much is it going to cost in total to take 20 lessons? So use the skills that we have been discussing to solve that problem. All right, enjoy.